Hi once again. What we are doing, we have already found a mathematical model of a second order circuit, which is this. We have done this. That was second order this one, and we found the state equation for this circuit, which is this one. Now the next step is to solve this equation. So how we are going to solve it? There are two alternatives. One of them is the mathematical solution. This is the one that you use in the differential equation course. So we will be repeating this one. That's the one. And the other one is, as you remember from the first order circuit, we are going to find the natural solution and the first solution, add them up and find the general solution. We are going to do this one later on. Now at this moment, what we are going to do, find a mathematical solution for a second order circuit. In order to find a mathematical solution of a second order circuit, we have chosen the circuit that we have already found. That's the state equation. So we're going to find the particular solution of this differential equation and then find the particular solution, as I said, and the homogeneous solution. Add them up, we find the general solution. So the first step, find the homogeneous solution. So I will be explaining in this video this homogeneous solution now, for which circuit I'll show it to you. So this is the circuit, that's the differential equation of our circuit, second order, and then we're going to find this differential equation solution. Now let me write what it is. It's going to be xt solution is equal x homogeneous plus x particular. So this is t, that is t. So this is general solution, general. So we are saying now we will be calculating this homogeneous solution now. As we know the differential equation course, in order to find what is general solution, then homogeneous solution is the solution when the knowns are equal to 0. In here, known is independent sources current or voltage. So that means this term is going to disappear. So what is left is this dVct over dt, dIL over dt is equal minus 1 over RC minus 1 over C 1 over L 0. That is A matrix. VCT ILT. So solution of this circuit, this equation is going to be X homogeneous. How we are going to find solution of this? We are going to estimate an exponential function and try to find the parameters that we see in this exponential function. So it's going to be a solution like that. Xt is k times a to the power st. So there are two parameters, this and this. When you are talking about k, so x has got two unknowns. This is capacitor voltage, inductor current. So x has got two of them. So it's going to be, so you can write this, maybe if I write it that's a little better. V C derivative, IL derivative is K1, K2 e to the power st. That's our estimation. So I will be calculating that case, trying to find this s and the case. So how I am going to do it, we are going to put our estimated function, solution function, into the differential equation. So you're going to take the derivative of this. So consider this one, that makes it a bit simpler mathematically. So derivative of this one is k s e to the power st is equal, that is a, times this, that is x, isn't it? So k times e to the power st. Since I know e to the power st is different from 0, so this disappears. And if I replace s1 on the left hand side, this is going to be s I will explain what I is, minus a times k equal to 0. I is a unit matrix. Unit matrix is this. Diagonal elements are 1. So Si is S0, 0, S. Why needed to do that? Because this A matrix is a square matrix. If you consider this is a scalar, so you cannot subtract a 2 times 2 dimension matrix from a scalar. So this, in order to make an operation, that is differentiation operation, subtraction operation, so this matrix should be at the same size. So that makes it the same size. The order of this is 2 times 2. The order of A is 2 times 2. That. So equal to 0, what happened is this. This became a linear equation now. Why it is linear? So these k's are unknowns. We are looking for to calculate that. And s also is unknown. So if you are calculating k's unknowns, this is a linear equation, isn't it? There are two unknowns, k1 and k2, and we will be calculating this k1 and k2, two unknowns. If we know the s, so we know that if there is a homogeneous linear equation like that, so I'm talking about some information that you have seen in linear equations course. The solution of a linear equation like that, if the determinant of this matrix, square matrix, is equal to 0, is not equal to 0, that means different from 0, that means you can get the inverse of this matrix. If you get the inverse of matrix, you're going to multiply this inverse matrix with 0, gives you 0. So the solution becomes 0. When k solutions are 0, that means your estimated functions become 0. Any 0 function is a solution of your differential equation, but it has no meaning. So we call it in English trivial solution. So we are looking for a non-trivial solution. That means a solution which includes a form like that. So that means k's should be numbers in it. So how I am going to calculate those? We say we get the 0 solution if the determinant is different from 0. If the determinant equal to 0, so let's do it here. Si minus a determinant is equal to 0. What does this mean? You cannot get the inverse of this matrix. That's one solution. One conclusion. The other conclusion is this. These equations, there are two equations here, they are linearly dependent since the determinant equal to 0. If they are linearly dependent, so this is a homogeneous linear equation. Just remind you a bit linear algebra. An example is this: x minus y is equal 1. If I multiply this equation with 2, 2x minus 2y is equal to. So this is a dependent equation, that is. Because I get this is linear dependent of this one. So we have seen in linear algebra course that the solution of this is also the solution of this. So I do not need this. If you don't need that, take this out. So your homogeneous, to make it homogeneous linear equation, so it's going to be 0, isn't it? Let's make it 0. So I am correcting myself here to make it similar to the one that we have seen here because of that. So this homogeneous equation is equal to 0 and linearly dependent those two. And then how I am going to find the solution, x and y. The number of solutions are independent. I'm going to make this one. Okay. So from that, what you get is this, x equal y. So you can find infinite number of solutions to that. How you can find it? If you say that y equal 1, x equal 1. Is y equal 2, x equal 2. So there are many of them solutions. So I was looking for K1 and K2 values, but I have seen many solutions to that. So I accept that. And how I am going to choose the one that I am dealing with will be to use the initial conditions. I will explain it later on. But this conclusion, when this determinant equal to 0, conclusion tells me that the case that I am looking for is infinite number of sets that I can find. So leave this as it is and come back to this now. In order to say that, this determinant must be equal to 0. How we are going to calculate this determinant? Let me do it here. Si was this. That is A. So that is A. So I am going to subtract that A matrix from this matrix. What you get is S plus 1 over RC minus 1 over C, 1 over L, and S minus 0, S. So this is the determinant of this matrix now is equal to 0 determinant. So I'm going to multiply these two and subtract those two. Then it becomes S square plus 1 over RCS plus 1 over LC equal to 0. This is called characteristic equation. So you can remember it from the differential equation course. So this is second order equation. So there are two roots for that, and these roots are. So at the end we are going to divide it by 2a. A is the coefficient of this, which is 1. So at the end I'm going to divide it by 2. So minus b 1 over rc plus minus 1 over r square c square b square minus 4 1 over LC. So I said I am going to divide it by 2. So when you divide it by 2, it's going to go in here and make it 4. And in here this is going to disappear. Now this is the characteristic roots. There are two of them. So conclusion is quite interesting now. We were expecting to calculate a S parameter here, and we have found there are two of them. So if there are two of them, so this is going to be now, if I put S equal to 1, if I replace this S1, one of the characteristic root here, it's going to be like that. S1I minus A. So this K1 For this S1 characteristic root is going to be K11, K12. They were two, but in this case, for each characteristic root, there are going to be two of them, like that. So that S1 here is going to be a number, because these are RLCs are all the element parameters. So S1 is a number. So this is a square matrix. And I know since the determinant is equal to 0, these are linearly dependent. So you can calculate one of them from the other one. So it's going to be K11 is equal to alpha times K12. This is the example that I show you here. It is similar to this one. So this became very simple. The coefficient became 1, but in this calculation, this alpha is going to be different from 1 in general. It's going to be but a coefficient. So what this means, although there are two parameters in here, just one of them, in practice there's just one of them. If you replace that K11 with alpha times K12, so it's going to be just one unknown here, one equation, one unknown, so you can calculate one of them and calculate the other one. For the S2, I'm going to repeat the same again. In this case, it's going to be now K21, 1, 2, so the second one this is, and K22 equal to 0, and this K12 is going to be beta times K22. Why it is this? We said that determinant is equal to 0 because I calculated from that rule. That means these are linearly dependent, so that means one of the variable can be calculated in terms of the other variable, unknown or variable, whatever. Then there is going to be a relation like that. So remember that what you found here is the eigenvector. And these are eigenvalues. For each eigenvalue, you've got one eigenvector. In the vector, these entities are related to each other like that because the determinant of this is equal to 0. So let's come back to our original problem now. Homogeneous solution became what? X homogeneous is going to be like that. VCT ELT is equal K11 K12 e to the power S1t and K12 K22 e to the power S2t. I said this K1 and K2, so you can consider this first one, this K1. So the first indices here is 1 and the second indices is 2. 2 comes from this second characteristic root and 1 comes from the first characteristic root. So this is our homogeneous solution. Now when you look at it, on the other hand, we have one conclusion it's saying that these two is not two different parameters. These are two parameters. It is going to be just one because there's a relation like that between these two. So from this one, there's going to be just one parameter that we don't know. Calculation of these parameters is going to be done at the end by using the initial conditions, as we have done it for the first order circuits. So at this moment, we have calculated this S1 and S2 as the characteristic root. And what is unknown is the calculation of these K12 and K22. Once you calculated this, you can calculate this one, so you can calculate all the parameters here. So two parameter calculation is required, and since we've got two initial conditions, one of them is this inductor's initial condition I0, And the second one is the initial condition of the capacitor V0. By using these initial conditions, I can calculate the two parameters that I just mentioned here. So that is the end of this video then, so we can stop the recording and escape here. Oh, sorry. Escape.